Alright, so in a few videos we're going to start looking at sort algorithms, and it would be really helpful for us to be able to compare the performance of one algorithm against another algorithm. So you might think that one way we could do that is to implement one algorithm and then put a line of code that records the start time and then run the implementation and then have a line of code that records the end time, and we can subtract the start time from the end time and we get the running time of the implementation of that algorithm. And then we do the same for another algorithm and we just compare the two. Sounds great in theory, but unfortunately that's not a good way to do it because of hardware. Hardware is going to influence the running time of these algorithms. I mean, think about it. If we were to run an implementation on a desktop computer that was built in 2017 and compare that to the running time of the exact same implementation on a desktop computer that was built 20 years ago and perhaps is an old Pentium computer, or we'll even go further than that and run the implementation on a Commodore 64 or something like that, obviously the implementations are going to run slower on the older hardware. And if we were to run an implementation on a supercomputer, it's going to run really, really fast, even though it might be a really inefficient algorithm. So we need a more objective measure than just the straight running time. And so what we do is we look at the number of steps that it takes to execute an algorithm. And we call this the time complexity. There are two types of complexity. There's time complexity, which is the number of steps involved to run an algorithm, and then there's memory complexity, which is the amount of memory it takes to run an algorithm. Now these days, because memory is so cheap, memory complexity isn't such an issue. So these days we mainly concern ourselves with time complexity, so we're interested in how many steps does it take to run an algorithm. Now when we're doing this, we like to look at the worst case. Looking at the best case doesn't help us because you're rarely going to have the best case. Now we could take the average case, but that's not going to tell us the absolute worst time complexity. So if we want to know what the upper bound is, like what is the absolute worst that we can expect from this algorithm, it's much more helpful to look at the worst case. So it's helpful to compare the worst case scenario for one algorithm against the worst case scenario for the other algorithm. And so that's how we do it. So let's look at the algorithm that I have up on this screen. We've already looked at an algorithm for making tea, so now we're going to look at one little step, and we have an algorithm for adding sugar to tea. So in this algorithm, step 1 is to get the bowl containing the sugar. Step 2 is to get a spoon. So we're assuming we have loose sugar here. Step 3 is to scoop out sugar using the spoon, and step 4 is to pour the sugar from the spoon into the tea. And of course, if you want more than 1 teaspoon, then you have to repeat steps 3 and 4 until you've added the desired amount of sugar. Now we can see from this that the number of steps that it's going to take to add sugar to your tea is going to depend on how many sugars you want. If you only want 1 sugar, then this algorithm will run taking 4 steps. But if you want 2 sugars, it's going to take 6 steps because you're going to have to repeat steps 3 and 4. So let's have a look at what happens for the number of sugars. So if you have 1 sugar, you just need to do 4 steps. If you have 2 sugars, you're going to need 6 steps. If you want 3 sugars in your tea, you're going to need 8 steps because you're going to have to repeat steps 3 and 4 3 times. And if you want 4 sugars in your tea, I'm sure most of us would have bailed by now, but I do have a friend that I say takes tea with her sugar rather than the other way around, so she might actually make it down to row 4. If you want 4 sugars in your tea, then you're going to have to repeat steps 3 and 4 4 times. And so you're going to take 10 steps to put sugar in your tea. So as we can see, the number of steps or the time complexity of our sugar algorithm depends on how many sugars someone wants in their tea. If they only want 1 sugar, it just takes them 4 steps. But if they want 4 sugars, it's going to take them 10 steps. So the time complexity gives us an idea of how an algorithm will perform as the number of items it has to deal with grows. So as we can see, as the number of sugars this algorithm has to add to tea increases, the number of steps required increases. Another way of saying this is it tells us how well an algorithm will scale. So how well will it do when it has to deal with 100 items versus 1,000 items versus 1,000,000 items? And we'll see that some algorithms will scale really well and others not so well. The more items there are, the more the algorithm's performance will degrade. Now the big O notation is a way of expressing the complexity related to the number of items that an algorithm has to deal with. And it's written as a capital O followed by an expression in parentheses. So let's work out the big O value for our sugar algorithm. So it's conventional to designate the number of items by n. So in our case, the number of desired sugars will equal n. And as we can see from our table and from our algorithm back here, the number of steps is going to be 2 times n plus 2. And the reason for that is you have to repeat steps 3 and 4 for the number of sugars you have, so that's the 2n, and then the plus 2 is steps 1 and 2. Now, as we've seen, when n grows, the number of steps grows. Now, notice that the 2, this is going to be hard for me to say, but the 2 2's in the 2n plus 2, they remain constant. They don't change as the number of sugars changes, and because of that, we don't consider them when we're coming up with the big O value. It's n that's influencing the number of steps, and so in this case, we say that the time complexity for this algorithm is O of n. And because the time complexity for this algorithm increases in a linear fashion, we consider this to be linear time complexity. So a time complexity of O of n is linear time complexity. And if we go back to our table, we'll see that we go 4, 6, 8, 10, and of course we're going to keep going 12, 14, 16, 18. That's a linear progression. It's a linear sequence. And so the time complexity of our adding sugars to t algorithm is O of n. So these are the big O values we're going to mainly see in this course. We have O of 1, which is constant time complexity, O of log n, which is logarithmic time complexity, and that's log to the base 2, not log to the base 10. So it's log to the base 2n. O of n, which is linear time complexity. And then we have O of n log n, which is n times log to the base 2n, and that's n log star n time complexity. And we have O of n squared, which is quadratic time complexity. You'll see that when we look at sort algorithms, the first few we look at will actually be quadratic. And the order in the table is in best to worst. So if you can use a constant time algorithm, that's way better than a quadratic time algorithm. Now, as I said, you heard me say O of 1 and O of n. That's how you say it. O of, and then the value that's in brackets. Now, when I was taught about big O notation, for some reason, the person teaching the information instead said O to the 1, O to the n. And so that was drilled into my head, and it's a hard habit to break. The big O notation, it's the sort of thing that you don't have to say most of the time. You're reading it or you're writing it. So the correct way of saying it is O of 1, O of n, O of log n, etc. But I am going to slip up occasionally and say O to the, because that's what was drilled into my head when I learned this material. And so if you hear me say that, if you hear me say O to the 1, O to the n squared, etc., just convert that to O of in your mind. Chances are you're never going to actually have to say this, ever. In my entire career, I never once had to say O of whatever. In fact, in my entire career, we never once discussed big O notation. I'm sure that depending on what type of application you're working on, that might be different for you, but in my career, big O notation was sort of a non-issue. It was never something that we needed to worry about. And so if you're talking to somebody and they ask you about big O notation or big O values, say O of. And if you hear me say O to the in this course, just convert that to O of. So now let's go over to Wikipedia so we can actually see the big O values plotted on a graph so we can get a visual idea of the differences between the different big O values. So I'm here at Wikipedia, and you'll find this image in the Wikipedia article about big O notation, and I've also included a link directly to this image in the resources section. This image was created by user CM Glee. And so this is a graph of some of the big O values, and this represents how an algorithm would degrade. Along the x-axis, we have the input size, so the number of items, and along the y-axis, we have the number of steps. So you can see for a constant algorithm, O of 1, which is in this violet color, as the number of items increases, the number of steps remains the same. This is just a straight horizontal line. So here's the number of steps, and this line isn't climbing at all as the number of items increases. So that's the best case. If you can get a constant algorithm, that's pretty much the best you can do. The next best thing is logarithmic, and notice that it's log to the base 2. And we're going to see some algorithms that have this time complexity. This is in a dark blue, and as we can see, it kind of starts off climbing, so as the number of items increases, the number of steps goes up, but then it levels off. And it's pretty much almost constant time. If you can achieve log to the base 2n time complexity, that's great. We're not going to see any with, I think that's the square root of n, but we are going to see some linear algorithms. We've already discussed linear time, and so here's the graph. This is in green, so if you have 10 items, you're going to take 10 steps, 20 items, 20 steps, It doesn't have to be an exact match like this. It's more pattern of growth. So if the pattern of growth is linear, it's a linear sequence, then the graph is going to look like this. And this is what it looked like for our adding sugar to tea algorithm. We didn't start at 0 steps. If you want no sugars, obviously there's 0 steps. But our algorithm is for adding sugar to your tea, so that assumes that there's going to be sugar added. And so the minimum number of steps for one sugar is 4. So we'd actually start at 4, but then we go 6, 8, 10, etc. And so it's a linear progression. Now this orange line is n log to the base 2n. So here we're multiplying log to the base 2n by the number of items. And we're going to see some algorithms that have this time complexity. So this is worse than linear because, as you can see, the number of steps required climbs much more sharply. And then, of course, worse than that is quadratic. And we're going to start out looking at sort algorithms that actually have a time complexity of quadratic time. And this is an even sharper climb. This is the red dashed line. And so if you have 10 items, it's going to take 100 steps because that's going to be 10 squared. And so if you have a quadratic algorithm, this quickly degrades. 1,000 items is already 1,000,000 steps. So keep this graph in mind as we look at the different algorithms. The absolute best is constant time. If you can't get that, you want logarithmic time, log to the base 2n. Linear time is still pretty good. Once you start getting up into n log n and n squared, you can see that the number of steps required rises sharply as the number of items increases. In conclusion, this is what you have to remember really, a big O notation gives us a way of comparing the time complexity of different algorithms in an objective manner, in a hardware-independent manner. Okay, so that's it for now for the big O notation. We'll revisit this as we go through the course. So I'll see you in the next video.